Hello everyone, today I'm going to go over question 4 from your practice exam, and in doing so we're going to go over interpolation and calculating and using residual properties. In this problem we have 1 mole of N-pentane and we're going to be increasing the pressure and temperature. And we have to calculate the change in enthalpy and the change in entropy using appropriate generalized equations. Additionally, we're going to be assuming that Cp is constant at 12 times R. One important thing to note is that we are at very, very high pressures, and we cannot treat this as ideal because of it. So getting into this problem, here's a little makeshift graph that I use to at least better understand it myself. So we have 2 different dots. The first dot on the bottom left is the initial properties and the corresponding enthalpy values. The second dot on the right has the higher temperatures and pressures and has a higher corresponding enthalpy value. What we want to do is we want to calculate the delta H across it and find the actual change in enthalpy between the 2 real points. But we cannot do this using a single equation. There's no equation that can just relate 2 actual properties. However, one thing that we can do is we can relate the 2 ideal properties. So if we treated these 2 points as ideal, as if they had the residual properties were 0, we could then calculate the delta H ideal between the 2. So that's really, really helpful, and that we're going to use that later down the line. However, we do have some disconnect between the ideal initial and the actual initial, and also the ideal final and the actual final. And that difference right there is actually the residual properties. So the difference between the 2 initial points, the actual and the initial, is what we're going to call R1, or the first residual. The entropy and enthalpy between the second 2 points, the final 2, we're going to call R2. And we can use these 3 points, so R1, the ideal, and R2, in order to calculate H actual using our workaround method. How are we going to do this though? So again, we want to calculate the H actual, but we can't do that using a single equation. But what we can do is we can calculate the delta, or the residual property between the initial point, then calculate the ideal change in entropy and enthalpy, and then calculate the residual between the final points. So it looks something like this. And this workaround works for any problem where both points are not ideal. So we're going to be subtracting the first residual because we have to go towards the ideal. Then we're going to be adding the ideal enthalpy, and then also adding the second residual point. So make sure you have that negative first residual. And we're going to be using that equation later on. So in order to find these residual values, we're going to be using the Lee-Kesler tables because we want to practice our interpolation skills. So we're going to be using omega and these different values that we can look up inside of these tables, and using equation 6.66 and 6.67 to relate them. So for the initial conditions, we'll be starting at 516 Kelvin, which will give us a temperature ratio of 1.1, and starting at 16.85 bar, which gives us a pressure ratio of 0.5. We can then look at table D5 in the appendix and use our corresponding PRs and TRs to calculate our H residual naught over RTC. So because we are existing between our PR is between 0.4 and 0.6, it's right in the middle. We have to go between these 2 points and interpolate. But luckily, our TR is 1.1 and it lies on the graph, so we only have to do a single interpolation. To do interpolation, it isn't actually as scary as it may seem. I personally dreaded interpolation a lot, but the more I've done it, the more I've realized it isn't as bad as I had originally thought. So here we have 2 different given points. And in order to go between, and we want to guess some point in between the 2. So I think of it, I go back to my Algebra 1 class back in high school and middle school. and we have 2 points and we want to guess one in between. So we have our given x1, which has a corresponding y1, and a given x2, which has a corresponding y2. For some random x inside, what do we think the corresponding y value will be? The most basic method to do that, to find this corresponding y value, is to just draw a line between the 2 points. And then you just bring this x line all the way up and then just see where it lines up. So around right here. So that means our y value is somewhere in between the 2. And that's exactly what interpolation does. And drawing that straight line is why it's called linear interpolation. So we now want to find the y value at this given x point. So how we do that is we use point slope form. Point slope form is we take our y value that we want to find, and then everything else is known. So we have our slope here, we multiply it by the change in x, and then we're going to also add in this y1, this start point. Another way to rewrite slope is rise over run, because we're given these 2 finite points. We can subtract the given y2 from the given y1 all over the given x2 minus the given x1. Add in the change in x between the desired x and then the actual tabulated x, and then add in our initial y value as well. And this is what we're going to use to find our y, our desired value. So bringing that back to the problem. Again, we exist at tr is equal to 1.1, and we want to find what value of hr exists between 0.4 and 0.6. So to do interpolation, we're going to be calculating the change in the y value, which in this case are the numbers given, which is our hr naught over rtc. And then we're going to be dividing it by the given table values for the PR, so 0.6 to 0.4. Then the change in PR from the problem. So again, we start at 0.5, and then we're going to subtract the 0.4 from the table, and then add it to the starting value, which will be this negative 0.367. Getting values to it, again, this first value is the final point, I guess. So negative 5.81, and then subtracting the negative 0.367, which becomes a plus. The PR of the tables are 0.6 to 0.4, so that's what we have in their denominator. And this chunk is what is the slope. Then we want to find the change in PR from the problem. So we go from 0.5 all the way to 0.4. And then we're going to add the corresponding value from this, from that 0.4. So that 0.4 corresponded to negative 0.367. So we'll be adding the negative 0.367. Simplifying it down more, we get an HR naught over RTC to be around negative 0.4735. This seemed like it took a lot of time, but the more and more you do it, the more and more practice you become. It's really just finding the slope, finding the change in the given PR and the tabulated PR, and then making sure you add it on to the initial value given. So we're going to have to do this 7 more times. You have to find the HR naught for the initial point, the HR1 for the initial point, twice again for the final, and then also double that again for all of the entropy values. And then we can add them all together to find our HR initial all over RTC using our omega value, which was given in the problem. So now we're able to find all of our different residual properties at our initial point and at our final point. But we also now still have to calculate the change in enthalpy and entropy from an ideal gas. So in order to do that, we'll be using equations that you have probably seen a lot this semester. What's nice about this problem is that our CP is going to be constant, so we can take it out of both of these integrals, and it allows it to be much simpler. You don't have to do the A plus BT plus CT squared plus DT to the negative 2. You don't have to do that for this problem because CP is constant. You can take it out of the integral. So doing that, we can get a delta H for the ideal gas to be around 13,000 joules, and our ideal S change to be around 21 joules per Kelvin. Then we can add in our equations that we calculated earlier, the negative first residual plus the change in the ideal plus the second residual. So doing that for enthalpy gives us minus negative 2000 plus our 13,000 plus our negative 1400. And that gives us an actual enthalpy change of around 13,900 joules. For entropy, we'll be subtracting the negative 3.1, adding our ideal change, which is 21, and then adding our negative second residual, which is negative 1.74. That gives us an actual entropy change of around 22.6 joules per Kelvin. Additionally, the reason why I know the units of this are in joules is because of the R constant we used. We used R is equal to 8.314 joules per mole per Kelvin, and we'll be operating with just one single mole of N-pentane. So we can just have that all cancel out, and then sometimes we're multiplying by Kelvin, which is why our enthalpy doesn't have the Kelvin term in it. I hope this problem helped at all. If you have any questions, shoot me an email. And if you can, please fill out this survey. It's really important to us in improving our ability to assist you as a teaching assistant. Many of us will also be TAs for the future, so this feedback can also help you later down the line as well. Hope you all enjoyed the video, and again, let me know if you have any questions, and please fill out the survey. I'll post the link also in the description below. Thanks.